Okay, so this is day 4 of the extension unit. This was the extension to chapter 8. So I'm going to put chapter 8 extension unit. This is the day 4, and we're going to talk about domain and range in reference to exponential growth and exponential decay. Okay, so first thing we're going to do is review domain and range. So the domain is all possible x values, and sometimes those are called inputs. Not often anymore, but they used to be referred to as inputs. So that's your domain, all possible x values. It could be a list of values in roster notation, or it could have an inequality like all values greater than 1. There's a lot of ways to describe domain and range. Now, range is all possible y values, or sometimes referred to as output. All possible y values or outputs. Okay, so Roman numeral 2, growth functions. Here's a picture of a basic growth function. This is exponential growth. The equation here is f of x equals 2 to the power of x. What they don't show in the drawing, because it's invisible, is the asymptote. So let's draw in the asymptote. It's the invisible line that the graph gets infinitely closer to. It's dashed, it gets arrows, and you have to write its equation at one end. Y equals 0, either on the far left or the far right. If I had to describe the graph, other than the fact that it's exponential growth, we would say it is bounded below, which means there's a point at which the graph will not go down anymore. Now, it's not bounded above because this arrow keeps going on forever. It's just bounded on the bottom by the asymptote. The asymptote itself is a boundary, and since the line can never actually touch it, it gets infinitely close, it's called an exclusive boundary because the 0 itself is not one of the solution points. It just gets really close. So this is like the fence you don't own. This is the fence that bounds the property. That's your neighbor's fence, but it still is a boundary between you two. Now, in a basic exponential function, whether it's growth or decay, it's going infinitely left and infinitely right. So if you have to do the domain, it's pretty much everything because there's no breaks or gaps. So everything, remember, is all real numbers, which means no breaks or gaps. Now, the range, on the other hand, does have a limitation. It gets close to 0. The y values get close to 0, but they're never actually 0. So your range is y is greater than 0. Not equal to 0, because it never touches, but definitely greater than. So it goes above 0. So it can be super close, like 0.0001 or 0.0005. It just won't actually be 0. All right, let's look at example 2. Looking at this equation, which is right here, I have 2 to the x minus 1 plus 3. So remember your transformations, what's being done. If you add or subtract to the x, that's a horizontal translation. And it's always opposite from what you're looking at. So since it's x minus 1, it's actually plus 1 to the right. So horizontal translation plus 1 to the right. Now, outside of the x, there's a plus 3 added to the whole equation. If you add or subtract a number to the whole equation, that is a vertical translation. And when it comes to vertical translation, what you see is what you get. So this would be plus 3 up. So vertical is up or down. This is plus 3 up. Now, this is significant because with the vertical translation, which is the plus 3 up, Your asymptote, which was at 0, moves up with the graph. It goes up 3. And your new asymptote is the line y equals 3. This is going to affect your range because now your y values can't be 1 or 2 or 3. They have to be greater than 3 because the asymptote has moved up 3. So your range in this case is y is greater than 3. And you would get that from the graph or just from looking at the equation and noticing that there's a vertical translation up 3. So you don't have to graph it to be able to do domain and range. Now, the fact that it's gone +1 to the right, so it's gone right or left, doesn't actually affect the x values. They still go infinitely left and infinitely right with no breaks or gaps. So your domain is all real numbers. All right, flip the page. Okay, so this one is y equals 2 to the x plus 3. So again, we have that vertical translation. So without even looking at the graph, you know that the asymptote went from y equals 0 to y equals 3. So you know automatically your range is y is greater than 3 because it went up 3. Now in the graph, this is kind of what your grapher is going to show you. You notice it doesn't show you the asymptote. It won't. You as the math student have to know the asymptote's there, which is why you got to learn a lot of math before you can use a grapher. So this asymptote, even though it doesn't show up, moved up from 0. It went up 3. And now the asymptote is y equals 3. And again, you get that from the equation. Now, x values, infinitely left, infinitely right. On a grapher, they don't put the arrowheads on it. Again, you just have to know that the arrowheads are there. So this one will be all real numbers. Now, another way to write all real numbers is to put all and then a capital R with an extra bar on it. That's all real numbers. Or when you take your SAT test, their way of saying real numbers is they use a really, really bold R. It's just super dark. Capitalized, it's not italicized, it's regular font. And that's how the SAT says all real numbers when they do their multiple choice questions. So I wanted to make sure you put that in your notes so you know that's all real numbers. Okay, so let's look at number 4. So in this one, your base graph is the one where nothing's been done to it. So this is your base graph, which is y equals 3 to the x. And we're going to have 2 different transformations done. For this one, it's x minus 2, which means you're going to have a horizontal translation, and it's x minus 2, so it's plus 2 to the right. It's opposite what the equation says. Now, the other equation is y equals 3 to the power of x plus 2. So this one's going to go the opposite way. Again, if it's added to the x, it's a horizontal translation. And it's always opposite, so this one's minus 2 to the left. Now, moving the curve left or right does not change the asymptote. You can tell they all still get infinitely close to y equals 0. So the translations left and right don't move the asymptote at all, which means you're going to have your standard domain, all real numbers, and your range is going to be your default y greater than 0. All right, let's look at decay functions. Basically the same information, just the curve falls instead of rises. So looking at this one, it's y equals 1/4 to the power of x. You can tell it's decay because 1/4 is less than 1. And you can also tell it's decay because it's coming down. Now, just like growth, your decay curve has an invisible asymptote. So draw that in. Dashes with arrowheads at y equals 0. And it gets infinitely close the farther it goes to the right. So on this decay curve, it goes infinitely left, infinitely right. So the domain is all real numbers. And it's not been translated up or down. So the range is still all y values above 0. So y is greater than 0. Now, on this last example, you can tell this has been translated downward. It's kind of tricky to find the asymptote when it's been translated downward and you don't have the equation. But just remember, the curve should look almost exactly like the asymptote when you get out to the right. So look at the far right and draw your asymptote so it just barely hits that. And then you're going to be in the right spot, which in this case is y equals -6. So as far as domain goes, your values go infinitely left and infinitely right with no breaks or gaps. So all real numbers. But your range is different because I now have negative values. So my y values, my range is everything above -6. So it's going to be y greater than -6. With exponential graphs, your range will never be greater than or equal to because of the asymptote. It never actually hits the asymptote, so it'll always be just greater than. So you're never going to put that bar on. Okay, are there any questions?